If you tried to run today's instantaneous global internet on the database technology that ruled the 1990s, the servers would melt down. This is the structure of a relational database. For decades, it defined data within a strict grid of static tables, rows, and columns, linking a user to their purchase through a reference called a foreign key. To pull up a complete user profile, the system executes a join. The database engine has to physically scan and stitch together records scattered across multiple separate tables just to load a single page. That rigid grid makes evolving the software difficult. Adding a simple new feature, like a secondary shipping address, requires an engineering team to freeze the database and execute a structural migration, often causing hours of planned downtime. Traditional relational systems also hit a physical wall. They scale vertically, meaning the only way to handle more traffic is to buy a larger, more expensive host server with more RAM and a faster CPU. As user bases grew into the millions, the sheer weight of relational joins created a hardware ceiling. Tech companies reached a point where even the most expensive supercomputers on the market couldn't keep up with the processing strain. Breaking that ceiling required horizontal scaling, or sharding. Instead of one massive supercomputer, workloads distribute across hundreds of smaller servers. To make sharding work, engineers changed the data's physical shape. Systems like MongoDB abandoned tables in favor of BSON, or binary JSON documents. By embedding a user's profile, cart, and preferences inside a single self-contained document, the system eliminates CPU-heavy joins. Everything the application needs is stored in one place. To maintain high availability, MongoDB uses a replica set. A primary node handles every incoming write and instantly duplicates that data to secondary nodes. If the primary fails, the system promotes a secondary to take its place immediately. This flexibility makes it the standard for agile development. Content management systems and e-commerce catalogs use document models to push new features to users daily without migrating a rigid schema. MongoDB trades the strict rules of the relational world for development speed and horizontal scale, matching the pace of modern, evolving web applications. But high-velocity data presents a different challenge. Global IoT sensors and server logs generate millions of tiny writes per second, overwhelming even a single master database. Cassandra solves this with a column-oriented architecture. Rows have completely different column structures, growing dynamically. Its core strength is a masterless peer-to-peer design. Every node is identical. Incoming data strikes any node directly, eliminating central bottlenecks to maintain ingestion speed. The system uses an append-only log structure. It simply writes data sequentially to the disk as it arrives, avoiding the slow seek times of traditional updates and maintaining blistering speeds even under a massive global load. By removing relational complexity, Cassandra creates a fault-tolerant environment where global data ingestion continues, even if multiple servers in the cluster go offline. Traditional relational databases are still vital. For banking ledgers and financial transactions, where every decimal point must be perfectly consistent across the network, the strict rules of SQL are irreplaceable. We have entered the era of polyglot persistence. Companies no longer force one database to do everything. They use a mix of specialized architectures to solve different business problems simultaneously. A modern tech stack might use SQL for its core financial records, MongoDB for its flexible user profiles, and Cassandra to handle millions of high-velocity log entries. The billion-user platforms of today were built by matching the physical shape of data to the specific speed of the business. Architecture has become the primary limit on a company's ability to innovate and survive.